operator differentiation with respect to the algebra variable zeta. All right, and let's suppose if L is an element of AD. So what this means is L is equal to like A sub n d to the n A1d plus A0, where A0, A1, AN are algebra elements, so it's an algebra valued. This is a differential. It's a constant coefficient differential operator, but the coefficients here are elements of the algebra. Does that make sense? So if this and if there exists alpha in the algebra, such that L of e to the alpha zeta equals to 0, all right, then there exists L prime in the polynomials over the algebra, L prime such that L equals to d minus alpha L prime.
If L is in the, so you're saying L is an algebra differentiator operator of differentiation. Is that algebra? So L is inside the differential operators of an algebra. You need me to get off the chair?
And also, what did this thing do?
Okay. Oh, you're going shopping? I'm gonna get pranked on her.
What does it do?
Make that come down.
Ooh.
Benjamin, you've just invented the pulley.
Oh, I see.
It's just like a thingy.
A thingy.
A thingy is called a making a robot making. So it's just like the thingy. It's like the robot thing.
Oh. I will tell you, Benjamin, right now, this problem perplexes a lot of people in physics 1.
Pulleys. Yeah, really.
So you're way ahead of the game.
Go down, then skip.
And he has a stop too. Oh man, he's really ahead of the game.
Yeah, safety first, right, Benjamin?
Ladies and gentlemen, Benjamin has derived how to create a pulley.
So so I'm not. I think I understand my proof here.
Oh, okay, so we have L, which is a differential operator under the algebra.
Yeah, to say this is in here is to mean that it's a linear combination of finding the many powers of the derivative operator.
Yeah.
Mommy took Matthew to the doctor, buddy. worry, she'll come back and look at your machine before long. You're on borrowed time. It was only a matter of time before you became aware.
Should have said she was hiding.
You should have said she's hiding.
Yeah. Didn't go look for her. My boss an hour.
That's good stuff.
You just said you're the one that just makes
I do like to. I just my lies are usually more frivolous, like blue is red, red is blue, or scissors or donuts or something stupid.
Mom's
like that.
hiding because you're not really lying. She's not.
She's hiding outside of the house. The doctor's office, yes.
And okay, so I'm gonna skip ahead to this little section right here where the differential operator with respect acting on e to the alpha zeta is equal to 0. Then there exists an L prime, which is interesting to me that a differential operator has a prime.
That's just notation. That's just.
Okay, good. Oh, so
I blame Nathan.
yeah, I would change that to
Anything else?
M. Yeah.
Okay.
Or because L prime kind of insinuates that you're taking it.
I put that on my list of things to do before I submit this for publication again. All right, but
Okay, but yeah, so we have a second differential operator in AD such that L is equal to D minus alpha of a second differential operator. Okay.
So this is kind of like working sideways on the math we were just doing. It's like, well, we looked at d squared plus 3d plus 2, and we're like, yeah, d plus 1 times d plus 2, right? We just factored it, right? This would be like, I look at d squared plus 3d plus 2, I go, e to the minus t solves that. Therefore, I can factor out d plus 1.
Okay.
It's a kind of sneaky side thought, isn't it? But
Yeah.
let's see here if it makes sense. So this should give us alpha to the j, e to the alpha zeta, because every time you differentiate, you bring down the power of alpha by the chain rule, right?
Mm-hmm.
You know. And so if you think about L of e to the alpha zeta, which of course is p of d for some polynomial p, right? E to the alpha zeta, what happens is you just get p of alpha e to the alpha zeta, right? And then, of course, the p of alpha, you can, let's expand on what that means. That means like an alpha to the n plus a1 alpha plus a0, all that, times e to the alpha zeta equal to 0. So here I'm just saying that, I'm assuming that this polynomial is a(n) d to the n, a1d plus a0.
Oh, so alpha's a function.
Alpha is a number.
Ooh, alpha's not a number.
Just a number. It's a number which must appear as, so like alpha must solve what? It must solve an z to the n plus a1z plus a0 equal to 0. Now how do I get that? I mean, remember e to the alpha z is a unit.
Unit?
Because e to the minus alpha z times e to the alpha z is e to the 0, which is 1. I can multiply this equation by e to the minus alpha z, and I just get this is equal to, this times 1 equal to 0 times is equal to 0. So in order for this product to be 0, it must be that that characteristic equation has the solution alpha.
That has to be equal to 0. I'm with alpha is a number. Why do you have to rewrite it? If alpha is just a number to raise to a power.
Oh, why do I have to rewrite this?
Mm-hmm.
I'm just swapping out the alpha for z to show that, like, there's an equation, not in the differentiation operator, but just in like the variable of the algebra z, which has, if I plug in alpha as a solution, I mean alpha is a zero of this polynomial equation in the algebra? I could put alpha to the end plus a1 alpha plus a naught equal to 0. That's also true. But
Does alpha must be negative then? Unless you're talking about, oh, no, that's only if assuming positive coefficients.
I mean, alpha could be a 3 hyperbolic number or something.
Oh, yeah, you got that.
It's
I forgot we're working on.
so.
Yeah, you're right.
Now, then I'm referencing a theorem which I'm far enough away from that I doubt the theorem. But here's a theorem that I can claim, and then we can ask ourselves the question: how do we know this to be true? But theorem, if you have, P of z, an element of the algebra polynomials in Z, right? And P evaluated at alpha equals to 0, then P of Z is equal to Z minus alpha times Q of Z for some Q of Z polynomial in Z, coefficients in the algebra. In other words, factor theorem. So do we have a factor theorem?
A factor theorem?
Is there a factor theorem?
Like, you're talking about like a fundamental theorem of algebra? Or you're talking about
Like the factor theorem from like pre-calculus, right?
that any n-degree polynomial can be factored out?
No, the factor theorem says that if f of c is equal to 0, then x minus c is a factor. What's up, dude? You're looking for mom. Mr. Audric thinks she might be hiding somewhere. You should probably look for her in like the guest room, maybe under the bed. What do you think about that?
No, him dad's at the doctor.
What if mommy was hiding in Hannah's room?
No.
That would be funny, wouldn't it?
No.
Probably good to go check though.
Okay, so if f of c equal to 0, then f minus c is a factor?
If f of c equals to 0 for a polynomial f, then x minus c is a factor of the polynomial. How do we, is that true for polynomials over algebra? If it is true, right? If it is true, then
Wait, then f minus c is a factor?
yeah.
If f of c equal to 0 for a polynomial, then f for polynomial f, then f minus c is a factor?
Not f minus c, x minus c theorem.
Oh.
If f of x is an element of polynomials in x
Yeah.
for R, and f evaluated at c equals to 0, then x minus c is factor of f of x, meaning that f of x is equal to x minus c times g of x for some polynomial g of x. Right? That's the factor theorem.
Someone knocking.
It's actually true for complex polynomials, just the same. You know? What is it, Benjamin?
I don't see that.
You gotta keep looking.
Like, for example, somebody tells you you've got a third order polynomial such that, f of 1 is equal to 0, f of 2 is equal to 0, f of 3 is equal to 0, then you know that the polynomial is factored to x minus 1 times x minus 2 times x minus 3. And then there's like a constant in front because you can't.
Oh, yeah. Oh, I'm dumb.
I know you know this.
Sorry, yeah.
Now the question though.
I was thinking way too hard about that.
Right, I know, I wrote it in a kind of sideways way. So here's my question is,
Oh.
how do we know this?
That can't work over an algebra because you have zero divisors.
Well, that's the question is, that's my question is, does zero divisors get in the way or not? I mean, I don't know. Let's think through it, So, what comes before the factor theorem? There is the, what theorem?
What, factor theorem?
Mm-hmm.
Oh, wrong over here.
I gotta use my chalkboard sound.
You gotta justify buying it.
Yeah, I spent like,
Spend time and money.
I mean, I think I spent like, what was it? $10 whole on this chalkboard, so I guess it was 14.
You gotta at least use it for an hour.
Something like that.
That's how much I got paid when I was working at Chick-fil-A.
Now, I would have a very negative review of this chalkboard, if not for one fact.
What?
You introduced me to, the chalk.
Oh,
So with the chalk.
I'm glad that at least I can leave you with that, if anything.
Oh my goodness, like that was a significant event. Like, because no, seriously, like without that chalk, I don't like chalkboards. With that chalk, I love chalkboards. It's a game changer.
So I'm glad that I made a contribution to your life. There's a story about the Egyptian old religion that the gods would ask you 2 questions once you died. Have you experienced joy, and have you brought joy into someone else? And on your answer, so I know at least I got one of those.
oh, for sure.
I've
Yes.
given you joy with the chalk.
Very, very much so. So the thing that comes before the factor theorem is the remainder theorem. So the remainder theorem says, give a polynomial f of
I
x.
remember,
And, like, suppose you're basically trying to write f of x as multiples of some other polynomial. Let's call it p of x.
Mm-hmm.
So if you're trying to write it as multiples of p of x, the remainder theorem basically says you can do that. You can just take like q of x multiples of p of x, but you can't always just do just that for a given polynomial.
Yeah, you're gonna always have some extra left over.
Right, you got this remainder term.
Yeah, that's where we get synthetic division or long division from.
Uh-huh. Yeah, exactly. This essentially is long division.
Yeah.
And so, but the deal is that the degree of p is greater than the degree of r.
Always greater than, like not greater than or equal to?
Greater than.
Okay.
So like if we're dividing by a quadratic, the remainder term has to be at most linear,
Yeah.
If you're dividing by a cubic, the remainder term has to be at most quadratic. So, this, if you know this, and so you're like, okay, so f of c equals to 0, right? Well then, so, divide by p of x equal to x minus c, right? And so that would give you f of x equal to x minus c times some q of x, right? Plus the remainder term. Like suppose f of c is equal to 0. So use long division, or what we usually call the division algorithm in theory of polynomials. So that's the first question, is do we have a division algorithm for polynomials over an algebra?
Yeah.
Why or not? And so there's this, right? Now if f of c equal to 0, well, you plug in f of c, what do you get? So you see r equals to 0, right?
Yep. Oh, therefore, then that implies the other form, yeah.
Therefore x minus c factors. So but the remainder theorem is sort of a precursor to that. The remainder theorem simply says that, the remainder theorem says if you divide a polynomial by x minus c, the remainder is f of c. That's the remainder theorem. But anyway, the larger point is the factor theorem is proved by polynomial long division. The question is, what justifies division?
Oh, do we not have a definition for what division is over in algebra?
Well, how do you know that there exists, how do you know that there exists a remainder here?
Because
So
it's indivisible after a certain point?
Well, I mean, let's take it back another step. You have the integers, right?
Yeah.
You take an integer p, or let's say integer, I'll call it f.
Mm-hmm.
You can write it as p times q plus r, right?
Yeah.
And we'll keep it positive here.
Dad,
Yeah?
can I talk to Mom?
Can you talk to mom?
Yeah. Isn't Mom at the doctor?
What kind of mental powers do you have?
Something.
Like, I don't know. I mean, can you talk to... Probably not, because she's not going to pick up the phone at the doctor's office, because you know how doctor's offices are.
Oh.
Yeah. So, anyway, everything, suppose we're working with positive integers, right? How do you prove that? I mean,
You can rewrite an integer in this quotient variant.
so you're given f and a divisor p where p is less than f, let's say, right?
Mm-hmm.
The question is, how do you know that there exists?
Oh, I mean, you could easily prove that if you take p minus 1, you can just multiply it by 1, and you always will have a remainder of 1.
I think you're assuming the algorithm of division.
No. So f, right? You give it an integer f, take 1 away from it,
Yeah.
then you get a new number, let's say k.
Oh.
K times 1 plus 1 will give you f. And you can do that for any integer.
Oh, but I'm given this and that.
Oh, you're given f and p.
F and p. The question is, why does there exist a q and an r
Oh.
such that the r is less than p?
Is p also an integer?
Yeah. Why there exists, q and r in z such that r is less than p. Okay. And I'm keeping everything positive here, so
Yeah.
well, let's say positive or 0. So, 0 less than or equal to. How do you, this is the division algorithm, how do you prove it?
Give me a sec. I think I can crack this. Given that f isn't prime, it's always going to be divisible by 2.
Well, we don't know, I mean, f is...
Oh, yeah. Well,
so how about
you're
this?
given a p, though.
We look at, let S be a set.
Yeah.
Right? And let F be the set of F minus, let's say, P, I'll use X here just so it doesn't seem related. I could do T, whatever,
Mm-hmm.
PT, such that T,
We can't assume, division's a thing, right?
that's right, we're trying to prove that it is a thing.
Yeah.
So let S be the set of the given integer minus multiples of P.
Yeah.
Right? Now, this is a non-empty subset. And I think I can do, and I want to do more. I want to assume where, that I'm going to say this intersect with, since I've made a poor choice, since it's hard to erase.
Yeah, but...
So, positive. I want to choose all such positive numbers.
Yeah, no, but you run into a problem. You get remainders.
Well, that's not a problem. I mean, this set has possibly many things in it, right?
Yeah.
Like it has at least one thing in it, right?
Yeah, 0.
No. F minus p. What do we assume about f and p?
It has that's non-zero.
Right. In fact, f minus p is positive. So that means there's at least one positive number in here,
Yeah.
which means that it is non-empty. It's also integers. This is a non-empty subset of positive integers. Alright, what just happened? What? Oh, hey. Wow. Good job, Benjamin. You made mommy come back.
I'll cut this up.
You're looking funny. Welcome back. You became aware of your non-existence about 15 minutes ago, but Audric had a helpful suggestion. He said that he should just try to find you. I should have told him mommy's hiding.
I'm so good.
You have a bright future as a parent, Audric.
I hope so.
That's a quality dad lie right there. So the point is that this is a non-empty subset of positive integers, so therefore by the well-ordering principle, it has a least member.
Yeah.
That least member it has to have a unique least member, right?
Yeah.
So we let by WAP there exists R and S smallest, you know?
Mm-hmm. You can put min, can't you?
Yeah. I mean, it is the minimum,
Yeah.
right? So R is equal to the minimum of S.
See,
And
do you
therefore
not run
R is
into...
equal to F.
Oh no,
minus
you don't run into that. Okay.
PQ for some Q.
Yeah.
And so this is how the division algorithm is proved for integers.
Yeah.
And if you really look at this set is just a set which models successive subtraction. It's because you're taking the integer minus p, minus 2p, minus 3p, minus
Yeah.
4p. And if you think about, like, at a basic level how division works, that's
Yeah.
what it is,
Yeah,
right?
it's repeated subtraction.
So as you think about how to prove the
Oh.
division algorithm
yeah.
for polynomials, you know, it's something like that, right? So we do something like, you know, see,
You run into I still think you're gonna run into a problem.
so you do something like S is equal to the degree of, you know, how's it go? You define the set, you build the set of integers using the degree function for polynomials is what's done.
Mm-hmm.
So if you look at the, you know, and so I gave you a copy of Thumb and Foot to look at, right?
Yeah.
It'll be in there for sure. The proof of the division algorithm for polynomials. Now, the proof is given for polynomials over well,
Well, I have it, I think.
you do?
Yeah,
That's a
actually.
good question. Is that
There you go.
in Thumb and Foot? What is it given for? See, oftentimes you'll find it given for like polynomials over with coefficients from a field.
Mm-hmm.
But that may actually not be like the most general context in which it can be given.
So, is there a function? The only thing is, does there exist a function in which it pops out zero divisors?
I think,
And I think that's where you could run into a problem.
well, let me put it in different,
Or factor into zero divisors.
that always what I'm looking out for, right?
Yeah.
So,
See, but then again, you might not run into that problem because if it factors into zero divisors, you can't it's not factorable.
so here's the question is the concept of polynomial degree does it still work
over
for polynomials over an algebra. Like, it's still meaningful to talk about the degree of a polynomial over an
If you
algebra.
have an algebra variable, then yes.
I would think so, right?
Yeah.
But what about the properties? Are the properties of the degree function modified in any way?
They could be, because look, if you have fc equal to 0, right? And yeah, like, okay, fc equal to 0, such that the factors of a particular polynomial, one of them is a zero divisor. Let's say, what do we have a zero divisor in the hyperbolic numbers, like 1 minus j, or something like that? You run into a problem because you wouldn't have a remainder, or you wouldn't, like, the reason it equals 0 is not because it it equals 0. It can equal 0 without being factorable.
Mm-hmm.
Or if it is factorable, it's only factorable by a zero divisor, which might still be okay.
Yeah, this is why I tend to believe that there is a gap in theorem 5.1.
See,
Which might not have been obvious to, like, it might not have been obvious to Nathan and I at the time because we were so immersed in working in the non-degenerate case that. But sorry.
no, you can look. I'm just thinking of how it would work, because if you can factor out a zero divisor, that still means it's factorable.
Well.
No, it would still have to be factorable, because that means you take a given polynomial, you take out its zero divisor, and then you're still left with another polynomial. It gives you 0, but it's still a polynomial. That's factorable. Maybe zero divisors help you, because you can all.
I mean, I think you're right about what you're saying. In fact, I think that's going to be exactly what you're saying. You're on point. And if we had f of z equal to 1 plus j times z, right?
Mm-hmm.
And we look at f of 1 minus j, we get but f of z is not equal to, I think, a constant times z minus 1 minus j. Unless it is.
Wait, where'd you get the bottom part from? F of z not equal to c.
I mean, this is the factor theorem would suggest that it's, I guess I could write the c over here, but it's like the factor theorem says if f of a constant, in this case 1 minus j is 0, then z minus the constant is a factor, right? But since this is a linear polynomial, the factor has to just be a constant, right? So the question is it possible, can you solve this question mark? Can you find a c such that this is equal to c times z minus 1 plus j? And, I mean, the answer to that question is, it's tricky. It doesn't look like you can, but I think you can.
Whoa. One sec. Oh, we can play with things though. Like if you get a 1 plus j, you can eliminate some terms. Let me see. Let me crack it.
Yeah, you fiddle with that. Let me try to find.
So the 1.
Yeah, I think it's mostly page 234, 235 in here. It doesn't have the proof either. Well, maybe it has the proof in chapter 9 actually. The degree of the product is the sum of the degrees. That only is legit in well, I can't say it's only legit, but it works if the ring is an integral domain. Integral domains have no zero divisors. So like our algebra definitely in general is not an integral domain. So yeah, chapter 9 talks about polynomial theory more generally.
I'm getting somewhere. I'm on point. Okay. You need a J term,
Oh,
because the J term is going to get you a J squared term, but it gives you so you need a minus J, but then you get a minus, so that will give you a positive J, but give you 1. Oh, and then you can get a.
see,
Oh wait, this might work. There's only. Oh yeah, okay, so that gives you plus J. Okay, so ZJ minus or plus J. ZJ plus J minus J squared. So I need a minus. That was J, that was minus J. I need a minus ZJ. Plus 2J. Oh, I need a 2. So what is this? Plus 2J squared. Well, maybe plus minus ZJ. Oh yeah, this should be minus ZJ. I need a plus ZJ. Minus J. Minus J. Plus J squared.
so page 299 to 300 is where the proof, the Euclidean, the division algorithm for polynomials over a field is given.
I keep dividing by 0. No, I don't divide by 0.
I think if you let C equal to, I want to say just 1 plus J.
I think I tried that already.
But is it 1 plus J times J minus 1, 0?
Let me do it really fast. 2, or Z, sorry. Z minus 1 plus J. Plus JZ minus J plus J squared. No, you get a minus 1, and you get this JZ term. So you get, you get a Z plus JZ term.
What one? Well, oh yes, but that's 1 plus j times z. So 1 plus j times z minus 1 plus j is 1 plus j times z plus 1 plus j times minus 1 plus j. But this is 0. So we just get 1 plus j times z again.
Ooh.
So factor theorem is not wrong. And this is not a counterexample to the factor theorem in the sense that we can factor f such that c minus c is, f of c, what I'm trying to say is f of c is equal to 0. And it did, in fact, imply that f of z is, z minus c times something else, right?
Sorry.
What's a bit unsettling about this, right, is the ambiguity in the ambiguity you have in.
See, but is this that's the only, see, but don't we want a general one?
Well, if this was going to cast doubt upon the factor theorem, this doesn't help us because, there is a factor corresponding to, c being 1 minus j. This is, z. This is. I'm using c in two different ways, but the problem here is just this 1 plus j times z, right? It's 1 plus j times z, right? And then plus any real number you like, lambda. Actually, not even any real number, any algebra number, alpha, right?
Yeah.
Times 1 minus j. You can put anything here because this times that is 0. And so this is just straight an identity. I'm just saying it runs counter to our intuition of matching coefficients for polynomials, right? If you have something like 3x plus 2 equals to mx plus b, we just look at it and go, oh, m is 3, b is 2. If I have cz equals to, b times z plus a or something like that, where a, b, and c are hyperbolic numbers,
No, that's not.
I'm not sure. I'm hesitant to say what I can say. Maybe I can say b equals to c. I think I can say b equals to c. Actually, so this is a good example of where calculus helps. And the reason I say that is if you have this, cz equal to b times z plus a, and suppose, again, a, b, and c are all hyperbolic numbers. If I evaluate it, z equals to 0, what's it tell me? It tells me 0 is equal to b times a. Now, in our ordinary experience in real and complex variables, so b and at least one of b or a is 0.
Yeah. But in hyperbolic, that could be 1 plus j, 1 minus
They
j.
can be a pair of 0 values. Now we differentiate
What?
that equation, what does it give us? It gives us C. Differentiate this with respect to Z. So the rules of calculus, they're still, you know, they didn't get messed up by zero divisors really. Pull the B out, right?
Plus A.
Well, what's the derivative of a constant, you know?
Oh, yeah. 0.
So the point is that this is B, so
Yeah. So just, no,
B does equal to C.
yeah. So,
So this is the tension with this stuff, is like I mean, it's tempting to say, oh, I can't say anything zero divisors, right? But that's also too lazy because it's not true.
yeah.
Like you can say things, you just have to be careful what you say.
Is that a proof though?
I mean, it's a proof that these being equal requires B equals to C, and that the product of B and A have to be zero divisors, yeah. So like if A is a unit, this is impossible. A can't be a unit.
The unit. What do you classify as a unit?
A unit is a element of the algebra which has a multiplicative inverse.
Oh.
So if A has a multiplicative inverse, that forces B to be zero. So unless I'm also giving C is zero, I'm in trouble. I mean, these are the kinds of things we can say. Now, so my question is, going back to like basics, how did we prove the polynomial long division rule, right? Because if the proof of that transfers to polynomials over an algebra, then we can use that and maybe work our way to a factor theorem. I mean, good that we didn't find a counterexample here. So the regular proof for polynomial log division, it's based on looking at a set of integers formed by the degrees of the polynomials in play. And you use the well-ordering principle on the set of degrees. Let me set it up. I'll do it over here because chalk is expensive. So again, on page 299 to 300 in Dummett and Foote is where the regular Euclidean polynomial long division is proved. But I'm not actually going to look at that. I just wanted to tell you that as a reference. Okay, so I think like the easiest thing to get started here is to do. So we're talking about f of x and p of x over. We'll keep it real for the sake of discussion. I want to like prove that there exists, q of x and r of x such that f of x is equal to p of x times q of x plus r of x, where r of x is equal to 0, or the degree of r of x is what? Is less than the degree of the thing we're dividing by, which in this case is p. I'm going to assume for convenience that the degree of p of x is less than the degree of f of x, okay? So we're like trying to divide a polynomial of smaller degree into f of x. So I guess we're looking at the set of like f of x minus what? Minus multiples of p of x, right? So I can look at f of x minus multiples of p. Now multiples of p of x would be something like, you know, I'll use the q again. I'll call it q bar this time. Q bar of x times p of x, right? Such that q bar of x is polynomial.
I wrote this down on this sheet of paper besides this notebook, so I better restart.
You're fine. P paper.
No, I just wrote down my notebook instead. Or wrote it down on this.
Now this set I'm currently looking at here is not, we can't use the well-ordering principle on this. I mean, this is a set of polynomials, right? But if we instead look at the degree, right? If we let S be, let me call this thing T, right? And let S be equal to degree of, you know, g of x such that g of x is an element of T. So that right there is a subset of, you know, the positive integers, right? Because degree is greater than or equal to 0.
Okay. I get what the words mean, but the set of degree of the degree of g. So you're talking about like if g is a
Something up in here. This is a typical g of x right here.
oh
I'm just giving a label to that.
okay. You're just giving a label to the degree of it.
The reason I'm doing that is because now I've got a subset of integers, positive integers, so I can apply the well-ordering principle, right?
Yeah. Yeah, that's what I was doing in my head. I was like, well, you know that there's so many spots where you're supposed to get crossing the x-axis.
Right, so we'll let, I don't know, r naught equal to the minimum of s, right? If you like. So, well, first of all, if 0 is an element of t, then f of x is equal to q bar of x times p of x, right? So we're done. Game over. Factored, right? Remainder 0. So, if 0 is not in t, right? Then So this is where you get into trouble with like I mean, I'm gonna be careful here because
Okay, well, you get a pass because only P and F. No, never mind. So wait, why? If you set P or Q equal to a constant function, you could get away with a lot more.
Oh.
No, never mind. Let me stop. Well, that would make sense because that would just be a thing. Okay.
Well, I mean, you might be right. I'm gonna say 1 is less than or equal to degree of P. I want to look at like, I'm interested in linear factors, whether or not this proof descends to the constant case or not. Look at separately, but it's funny stuff happens with constants, for sure. So, all right.
Yeah, but you haven't left a. Never mind. There you go.
All right. So suppose that suppose R naught is the minimum, and that's not equal to 0. Okay. So
Yeah.
set aside this case.
Okay.
All right. Then there exists Q bar, right, of X, such that, let's call it R of X equal to F of X minus Q bar of X P of X, right? And degree of R of X is equal to R naught.
Yes.
Of course, then F of X is equal to the desired, Q of X, P of X plus R of X. The question is, does the degree of R of X is necessarily less than